Okay, so now we have all the tools to start thinking about the notion of Shapley value. So before we get into details, let us just take a step back and just make sure that we all understand what we are trying to achieve here. So you're given a cooperative game, NV, and you know that different coalitions can form, right? So what we want to kind of say is that for each coalition that can be formed, how should the players basically share the coalition worth among themselves, given that this all these different coalitions can form, right? So the idea is that we are going to go and going to give a description of this game to an unbiased judge. Then the judge is basically going to figure out a way to divide the proceeds from this game if the players actually seek the judge's advice, right? So it's unbiased in the sense that it is not biased towards any one particular player. Okay. So we are going to kind of like look at this problem from several different perspectives. And the first perspective is to take a more axiomatic approach. This was first formulated by Lloyd Shapley, the same Shapley that we discussed when we were doing the Gale-Shapley algorithm a few weeks back. And the Shapley value is basically a theory to provide an answer to this question, right? So one of the answers that you can have to this question that the judge might pose about how do you go about dividing the proceeds of this game, right? So what it does is that it lays down rules that will enable a judge to actually suggest a way of allocating V of n. So this is the value of the coalition which consists of all the players among the different players, right? So this is the big picture view of what we are trying to achieve. Okay. So before we get into the fully complicated problem, let's just take small examples to understand the different parts that are involved, right? So let's consider this game, which is very simple. You have got four players, 1, 2, 3, 4, and the value of the coalition is equal to 60 if all the four players are in the coalition, right? Any other thing, the value of the coalition is going to be equal to 0, right? So this is the description of the game. So you can clearly see that in this case, all the players in this game are going to be symmetric, right? So here use the notion of symmetric players, but you can also observe from here, because the game is so simple, that there's no difference between 1, 2, 3, and 4, right? They're all the same in that way. Okay. So here intuitively, it should be obvious that the judge is going to kind of like suggest an equal division of this Vn equal to 60 among the players. And so the outcome of this game is going to be that each of the players are going to end up getting 15 each, right? Why is it intuitively obvious? Because if you have got fair division and there's no difference between the players, so then there's no reason for the judge to kind of like give one player more than the other, right? So this actually suggests our first two axioms that we are going to use to think about Shapley value. So the first axiom says that the total amount Vn, so this is the value of the coalition when all the players are in the coalition, that is going to be divided among all the players, right? And this axiom also has another name called the efficiency axiom. Okay, so why is this the a naturally obvious thing to have? So in a lot of games that we are going to consider, Vn is actually the largest amount of money that the players can get by splitting n into different coalitions, right? So what that means is that the players actually want to end up dividing among themselves everything in the game that they can achieve if they all come together, right? So this is basically this idea that you have this Vn, which is the largest amount of money that you have. Then it makes sense to kind of divide this largest amount of money among different players, right? So that's axiom 1. The axiom 2 says that if you have got symmetric players, and here we are using this definition of symmetric players that we just discussed, then each of these symmetric players must get equal payoffs, right? So this is known as the symmetry axiom, as you would imagine. And why would it make sense? Because remember, the idea at the end is to get a fair division, right? And this fair division has to be in some sense acceptable to all the players, right? So none of the players should feel that, it's being kind of like unfair so in terms of the reasoning that is being used. And if you end up giving symmetric players unequal payoff, right, then there's going to be kind of like a lot of jostling to be the one who gets the higher payoff, right? And also there would be reasons for the players to feel aggrieved, because they might be thinking, there's no difference between me and that other player, but why is that other player getting more than me, right? So if we want to think about it from a fair division perspective, then this axiom definitely makes sense. Okay, let's look at another example to see some of the other issues that are fairly straightforward. So you've got, imagine a 3-player game where V1, V2, V3 are all equal to 0, V1, 2 equal to 40, V1, 3 equal to 0, and V2, 3 equal to 0, and V1, 2, 3 equal to 40, right? So there are two things that you should note from this game. The first thing to note is that 1 and 2 are symmetric, right? How do you see that? So clearly V1 and V2 are the same. That's the first thing to observe. And the second thing you observe is that if you compare V1 3 and V2 3, you end up getting both 0, right? So if you just replace 1 by 2 or 2 by 1, that is not changing anything, right? So that's observation number 1. The other thing to observe is that player 3 is a null player, right? So how do you see that? So if you have v of phi equal to 0, if you just add 3 to it, you are still going to get 0, right? If you have got v of 1 is equal to 0, if you add 3 to it, you are still getting 0. If you are got v of 2 equal to 0, if you are adding 3 to it, you are still getting 0, right? And finally, v of 1, 2 is equal to 40. If you still add 3 to it, you still end up with 40, right? So basically, in this case, we see that, 3 is a null player and therefore is not contributing anything to any coalition that this person joins, right? So in this case, it's pretty reasonable to assume that player 3 should not get anything, right? Because player 3 is not contributing anything. So what you get from here is that player 3 should not get anything. Now, out of the 40, the remaining amount should be split between 1 and 2. And because 1 and 2 are symmetric using the previous axiom, we can suggest that perhaps they should get 20 and 20 each, right? So that the division of payoffs that you get is going to be 20, 20, 0, right? So notice how we used both axiom 1 and 2, and we used this new thing that again makes intuitive sense, that a player who contributes nothing to any collision should actually end up getting nothing as well, right? Okay, so this is axiom 3, which says that the payoff to a null player is 0. And this is also known as the null player axiom. And basically, again, it means that a player who contributes nothing should get nothing, right? So you can see here, by the way, how these different notions of symmetric players, null players that we just discussed are being used in this our discussion. And finally, we also discussed the sum of games. So let's take a look at an example to see how that comes into picture, right? So imagine that you have a two-player game, players 1 and 2. You have got v1 equal to 30, v2 equal to 20, v12 equal to 80, and v5 equal to 0, right? So here clearly you notice that neither 1 or 2 are null players, right? Because you have got that if you add 1 to v2, then you end up getting v12, so you have an increase of 60. And if you are adding 2 to v1, then you are going to end up getting 80 from 30, right? So in each case, there's clearly a value addition, right? The other thing you notice is that it's not that 1 and 2 are symmetric, because if you change 1 from v1, it becomes v2, and then the value actually is a different value compared to v1, right? So all these previous things that we studied are not necessarily going to help us, but let's kind of like consider a modified version of this thing, right? So you have this original game described in terms of V, but now let's think of like creating new games from this, right? So let's create the following three games. You have got the values U, W. So this is a typo. This should read W and tau. Okay. So if you now do that, what's going to happen is that U1 is created in this way. So the game U has U1 equal to 30, U2 equal to 0, U12 equal to 30. The game W has W1 equal to 0, W2 equal to 20, W12 is equal to 20. And the third game is tau. 1 equal to 0, tau 2 equal to 0, tau 1, 2 equal to 30, right? So we can represent the game in the following way, right? So this is the graphical description of the game. So 1 alone, remember, on the left-hand side, we have got V. So 1 alone can only create a value of 30. 2 alone can create a value of 20, but if they get together, they create a value of 80, right? So this is this game, original game V, right? Now we have these other three games, right? So which has U alone can create 30, 2 alone can create nothing, but 1 and 2 together can create 30, right? In this second game in W, we have got that 1 alone creates nothing, 2 alone creates 20, and 2 and 1 create 20. And in the third game, we get that 1 alone or 2 alone does not create anything. So this is the tau game that we just discussed. But 1 and 2 getting together creates a value of 30, right? Okay, so first thing to notice is that, is this a split of the game? So let's see. So you have got 80 here between coalition 1 and 2. And now if you add up these three things, you have 30 plus 20 plus 30, so which is 80. That is great. 1 alone is 30 in this original game. And here, if you now add up over the three games, you get 30 plus 0 plus 0. So that adds up to 30, right? And similarly, you have got 0 plus 20 plus 0, so that adds up to 20. And so therefore, you can see that this is clearly a split of the game according to how we have defined, right? Now, the question is, this is a split of the game, but why did we took this particular split, right? Is there any advantage? So remember, our objective is to kind of like understand what is the value of this original game V, right? Which is the one on the left-hand side. What we have done is split it up into these three parts. Now, what is special about this particular way of splitting things, right? So let's consider this first game, which is, remember this game U, right? That is the description here. And if you notice here, clearly that what you observe is that 2 is a null player, right? How do you see that? Well, V2 is equal to 0, right? And if 2 is to add up to 1 and create a coalition 1, 2, so compared to a coalition which has only 1, 2 is not contributing anything, right? In both cases, you have got V1 equal to 30 and U1 equal to 30 and U12 is equal to 30 as well, right? So there's no value addition that 2 is doing in any case. So then we can actually use our axiom, right, to suggest that in this case, actually 2 should end up getting nothing, right? So this is our axiom 3. And so therefore, this entire value that is being created in this game U should go to player 1, right? So 1 should get 30 from this player game U and 2 should get 0. Okay. What about the second game, which is the W game? So here, if you do the same bit of analysis, you notice that V1 is equal to, W1 is equal to 0, W2 equal to 20, and W12 is equal to 20. So again, the same reasoning would tell you that player 1 is a null player in this game W, and player 2 is actually going to get all this surplus that is being generated. So the payoff to player 2 is 20 and the payoff to player 1 is 0. Again, using axiom 1 and axiom 3, right? Okay. What about the last game, Tau? So here on their own, the players are kind of getting nothing, okay? And if they actually get together, they end up getting 30, right? So this would be a case where actually 1 and 2 are symmetric players. Again, you can check using the definition. And so therefore, our prediction should be that 1 and 2 should actually end up getting both 15 each, right? So we can then jot down that based on these three axioms and by using it to these three different games, U, W, and tau, what we found is that in the first game on the right hand side here, the payoff should be 30, 0. On the second game on the right hand side, the payoff should be 0, 20, and here the payoff should be 15, 15, right? Now we can add up the sum of these three games to get the total payoff in the original game. Remember, our original idea was to get a payoff not in this U, W, or tau, but in this original game V, right? And now if you add up, you end up getting 30 plus 0 plus 15, which is 45, and 0 plus 20 plus 15, which is 35, right? So in this case, in the original game, the payoff should be 45, 35. So this is actually our fourth axiom, which says that if we split the original game into sum of individual games, then the division of payoffs among the players in the original game should basically be the sum of the divisions obtained in the individual game, right? And this axiom is known as the additivity axiom. And the idea is to kind of consider a situation where you have got a set of players who are playing separately in each individual game, right? So in this case, what the players will ultimately get would be the sum of the players they get, some of the payoffs that they get in this each of these individual games. Okay, so let me just summarize what are the four axioms that we used. So we use this axiom of efficiency. The efficiency axiom says that Vn, which is the value of the coalition when all the n players are in that coalition, is to be completely divided among all the players. We have got the notion of symmetry axiom, which says that if there are symmetric players in a game, then they should get equal payoffs. We have got the null player axiom, which says that if there is a null player in the game, in the sense that it does not contribute to any coalition of which it is a part, then that player should get 0. And finally, we have the additivity axiom, which says that if you have a game and you have decomposed it into two games, then the value of the sum of these two games has to equal the sum of the value of the original game, right? So these are the different axioms. And what Lloyd Shapley did is that he actually proved that these four axioms actually will always lead to a unique value for any game that you are considering, right? So that is a more mathematical proof, which we are not getting into here, right? Instead, let us kind of like focus on thinking about how does this four axioms kind of help you to get an answer about, what is the different split that these different parties should get, right? So imagine that you have got a 3-player game. So you have got V1 equal to 6, V2 equal to 12, V3 equal to 18, V12 equal to 30, V13 is equal to 60, V23 is 90, and V123 is 120. And as usual, V5 is equal to 0, right? Okay. In this case, clearly what you should observe is that, there is no symmetricity, right? In the sense that 1, 2, and 3 are clearly different. You can again observe this from the first line, that if any coalition that has one member, if you just replace it by another coalition, the value is always going to change, right? And there are also no null players. Again, you can just kind of like see this from, again, this looking at this single player coalitions, because V5 was, remember, equal to 0. So anytime you're kind of like adding a player, that is kind of like leading to an increase, right? So from here, you can kind of like see that these are not null players, right? So the question is, what is our prediction about how this value is going to be split among the different players, right? So in particular, how this value 120 is going to be split among players 1, 2, and 3. And we want to use these axioms that we have developed to kind of like think. So if there are no kind of like symmetric players or null players, as we have discussed, probably the first thing to do is to kind of like then use axiom 4, right? Which is to think about a way of like splitting up this game into different games, so that we can then start applying these different axioms that we have studied, right? So how do we go about doing it? So this is one particular decomposition that we use. First, let us just understand what is this decomposition and what is the significance of this decomposition in terms of the value of the game for these different players. And then we'll later on discuss about how did we actually end up being able to split the thing in this way, right? So this is the original game V that you had, that is described here graphically, right? And then what we are doing is we are splitting this up, right, into actually 7 different games, okay? So let us note first whether this is actually a split or not. So for example, consider the original value of the coalition 1, 2, 3 in the original game, which was 120. So here, if you sum up the different values for 1, 2, 3 across these 7 games, you end up getting 6 plus 12 is 18, 18 plus 18 is 36, plus 12 is 48, plus 36 is 54, 84. And then you have got plus 160, so 144, but that has exceeded 120. So you need to kind of like subtract minus. So subtract 24, so you have got minus 24 here. So now if you add up all these things, you end up getting 120, right? Similarly, take anything else. So suppose you are looking at 1, 3, and if you add up across these 7 games, so you have got 6, 18, 24, plus 36 is 60, plus 0 plus 0 is 60, right? So you can like look at the value of any coalition and on the left hand side, and the sum of the values of this coalition for these different 7 games on the right hand side, and you will see that they're always going to be equal. So at least we should agree at this point that this is clearly a split of the original game into 7 different components. Now the question is like, how did this particular way of splitting actually help you, right? So let's take a look at the first example. So from here, what we observe is that you have got basically players 2 and 3 are going to be null players in this first game. And player 1, therefore, is going to get all the payoffs, right, using axiom 3. So let's see why we said that 2 and 3 are null players. So clearly you observe that V2 and V3 are equal to 0. And anytime either 2 is joining an existing coalition or 3 is joining another existing coalition, they are not increasing the value, right? So for example, if 2 decided to join 1, so that we have got V1, 2. So that's equal to 6, where the originally V1 was also equal to 6, right? Instead, if 2 decides to join the coalition which had 1 and 3, and therefore gets, we now have a coalition of 1, 2, 3. So again, the payoffs are the 6 in each case. So there's nothing that 2 is adding, right? And similarly, the same thing from 3's perspective. So 3 is also a null player, right? So that would suggest that in the first game, at least, that you have, 1 should get all the payoff, which is 6, and 2 and 3 should get nothing, right? Okay. We can then kind of also look and do the second case, so where you can do the same analysis and show that in this case 1 and 3 are null players, and so 2 should get 12 from the second game. In the third case, you have got that 1 and 3 are the null players, and 3 should get 18, right? So already from these first 3 cases, we know that what should be the payoffs. going to the different players, right? Okay, what about the fourth one? So here, basically, what we actually need to think about is the notion of actually symmetry, right? So if you observe that from here, basically 1 and 2 are symmetric, right? So they should split this 12 into 6 and 6 each. Here, what you observe is that 1 and 3 are symmetric, so they should split this 36 among 18 and 18. And here again, you observe that 2 and 3 are symmetric, so therefore they should split this 60 into 30 and 30 each, right? And in this last case, basically 1, 2, and 3 are symmetric, so they should split this minus 24 equally so that they get minus 8 each. So then basically we can use the Shapley value axioms that we just talked about, so that the Shapley value of every component of the split, we can compute that using the axioms. And how can we do that? Because in all the splits that we are considering here, all the players are either null players or symmetric players, right? So we can use basically axioms 2 and 3 there. And where are we using axiom 4? Because basically we are adding up all these things to get the Shapley value of the original game. Okay, so what's the value of the game? So again, as I mentioned, the first one will be 600. The second one will be 12 0 12 0 0 0 18 660 18 18 0 0 30 30 and minus 8 minus 8 minus 8, right? So if you now add up, 6 plus 6 is 12 plus 18 is 30 minus 8 is 22. So that's the payoff going to the first player. For the second player, you have got 12 plus 6 is 18 plus 18 is 36 plus 30 is 66 minus 8 is 58. So that's the amount that is going to the second player. And finally, the amount that is going to the third player is 18 plus 30 is 48 minus 8, so 40, right? And you can also see that these three things will add up to actually 40 plus 58, which is 98, plus 22 is 120. And 120 is this V123, right? So the first axiom is also kind of like verified in this case. Okay, so we have got this property. So given this game, this is the answer for what is the Shapley value in this case, right? Okay, so the only thing that we still need to figure out is that how did we actually manage to kind of like split this original game into these 7 components, right? So how, because that was a crucial step that we did not get into much details before. So let's think about steps one by one, right? So in the first case, imagine that this was the original game that you had, and you decided to split it off into these 2 games, right? So what did we do here? So we thought about from player one's perspective, right? So the player one, V1 is equal to 6. So figure out everywhere where you have got player one being part of the coalition, and then kind of like take out the value 6 from that, right? So you have got player one being a part of coalition one, so take out 6 and write it down here. Player one is part of coalition 1, 2, so write down this 6 here as well. Player one is part of 1 and 3, so write down 6 here as well. And player one is definitely part of 1, 2, and 3, so out of this 120, write down 6. And in the other game that you have, we are always going to be doing this split into 2 parts. What you're going to do is take the residual, right? So 60 minus 6, 54. 6 minus 6 is 0, 30 minus 6 is 24, 90 minus 0 is 90, 18 minus 0 is 18, 120 minus 6 is 114, right? So this is the first splitting. The second splitting, start out with this on the right hand side, this game that you have. So we have just written this down here. And now do the same thing that we did in the first step, but now do it for the second player, right? So the coalition which had only second player would take up a value of 12, right? So write the value 12 in this case, and any coalition of which 2 is part, subtract 12 from that part, right? So you have got again 2 is part of 1 and 2, so write 12 here. 2 is part of 2 and 3, write 12 here. And 2 is part of 1, 2, and 3, you write 12 here, right? And you get another new game, right? Well, you get 2 new games. One game we just constructed in this way. The second game, in order to do that, you have to make sure that that total addition has to be respected, right? So if you are assigning 0 here, you have to assign a value of 54 to 1 and 3 in this last game that we have here, right? Similarly, if you are taking away 12, so then 12 remains. If you are taking away 12 from 90, then 78 remains. 18 is 18, and then out of 114, you are taking up 12, so 102 remains. In the third stage, what you do is the same thing, but now with respect to player 3. So that means that you are going to have a game which is going to have 18 for the third player, 18 for coalition 1 and 3, which is on top, 18 for the coalition which is 2 and 3, which is this 18 you see here, and again 18 for coalition 1, 2, and 3, which is the 18 you see here. And again, you get in the new game, you have the residual, so that this is actually the sum of the games. Okay, so what's the general procedure that we are doing? So what we are doing, if you notice, is actually at every stage, we are splitting the game into two games, okay, which has a special property. So namely, it contains a coalition S such that Vt is equal to Vs whenever T contains S, but V2 is equal to 0 for every other coalition that you can think of, right? So this type of games are what are known as carrier games. And the coalition S in this case is called a carrier, right? You can define it mathematically as well. So basically, we are going to say that a carrier game NV is a game in which there is a coalition S called the carrier of the game, such that Vt equal to Vs whenever S is a subset of T and Vt equal to 0 otherwise, right? So if you can use this definition, and then you can kind of like go through this and see that in the first split, this first game, 1 was the carrier, in the second game 2 was the carrier, and this in this third game you have got 3 as the carrier, right? So this is how it follows. Okay, now that we have this game 36, 0, 12, 0, 60, 0, 84, the next question is how do you get the next split, right? And here too the answer is simple. Instead of now looking at single player coalitions, think about cases where the carrier has like 2 players in the coalition, right? So the first example would be 1, 2. So 1, 2 was generating 12, right? So every time you have got 1, 2 as part of any coalition, then you should kind of like write down 12 there, right? So 1, 2 is clearly part of 1, 2. So we have written down the 12 here. But the other coalition where 1, 2 are part is basically 1, 2, 3, right? So in this place, instead of 84, you will write down 12, right? So what about the residual? So the residual goes into this new game, so that you have again 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, 12 plus 12, 12 plus 0 is equal to 12. 36 plus 0 is equal to 36, and 72 plus 12 is equal to 84, right? So again, we are sure that this is a split of the game, right? How do you go about calculating the remaining calculations? It's the same procedure, right? The next step is to actually have applied to this game on the right hand side, right? Where you are perhaps considering 1, 3 as the carrier, right? So in that case, you would want to kind of like write this 36 in the new game as one value. You're going to take away 36 from this 60, and again from this 72, you're going to do 36, take away from that. And so this is basically the same procedure, doing it iteratively, right? So in the end, you are going to get this this one here by writing that 36. You're going to get another game which you can again split using coalition 2, 3 as the carrier. And finally, whatever is the surplus that is left over, which will be a symmetric game that is kind of like here. And so therefore you can apply all these axioms to kind of like do it in the way that we discussed, right? So one final point to note here. So this is one way of splitting the game. There may be other ways of splitting the same game, right? So it doesn't matter how you decide to split the game. In the end, you are going to end up with the same value of the what is going to the 3 different players, right? And this is actually one of the results that Lloyd Shapley had proved, right? That there is a unique value that is generated at the end, regardless of the way in which you split things, right? So here we, in this particular case, we split these things so as to make it easy to apply these axioms. But there are other ways of splitting it also, so that you can apply the axioms, right? The point though is that the final value is going to be the same, and that value is what is known as the Shapley value of this cooperative game.